All right, Algebra 2, welcome back, guys. We are in Section 2 today, Chapter 11. This is all about theoretical and experimental probability. All right, I know I said it in the last video, but here it is directly in front of you guys. Listen, key terms are important. Concepts are important. There's so much conceptual stuff in this chapter. This takes a very different, drastic turn away from like algebraic stuff where it's just a lot of computation and plug it in, work out the equation, get the answer. There's just so much more to deal with. What is the phrasing? What's the word? What's the special phrase that determines I use this, or something different that tells me I use this? All of that is to be said that, listen, you have to pay close attention to exact phrases. As this says right here, key phrases are there to guide you, but it takes practice, it takes repetition, and the note down here, practice, patience, and pay attention. You can't just skim through these problems unless they're, those real introductory easy type ones. But pretty quickly you get word problems in this section where the phrasing is just everything. Okay, so all that to be said, that there is just no room where you can afford to check out. Okay, and all the past years that I've taught this chapter, it really doesn't matter who the student is. Everybody has to work pretty hard to understand what you are coming up against because of all the words. It's not just like, here's the equation. All right, so there it was. Mr. A just said plenty of words right there for you. The page you're looking at, this is all your notes. Okay, so let's zoom in here. This section all about theoretical, which means a theoretical thing is like, this is what should happen. This is what, if we just crunch the numbers, this is what should happen. Experimental side of things, which we're going to be getting to right over there. The experimental side of things is like, this is what actually happened. We did the experiment. We conducted this. This is the real numbers, what we got. Okay, so that's the difference there. A real quick example would be, theoretically, when you flip a coin, you have a 50-50 chance, heads and tails. Okay, but the experimental probability could have this weird skewed data where you flip a coin and for whatever reason, 7 times out of 10, you landed on tails. And it doesn't seem like it should be that way. But the experimental probability says, well, that's 70%, when the theoretical probability is like, it's a 50-50 shot. Okay, so that's the quick difference definition that you're looking at. All right, so whenever you see this capital P, that just stands for probability. So this phrasing right here would say probability of event. All right, probability of what you are trying to have happen. Number of favorable outcomes, that's what you want. So favorable outcomes goes on top. Total number of possibilities goes on the bottom. So that's the total number. Again, if we're just flipping a coin, there's one side that's tails, so that goes on top, and the total number of possibilities is 2. So that's why it should just be 1 over 2, 50%. All right, so that's the basic on theoretical probability. Taking a look at experimental, it's just actual experimental, like what you got, the actual number of times the event occurs, because you did the experiment. And then on the bottom, just the number of trials, how many times you did it. So if we're going back to flipping a coin and we landed on tails 7 times, well, that's the number of times. 7 over, how many times do we flip a coin? 10. And 7 over 10 would just be a 70% chance. Okay, so there we go. This information right here gives you a little bit more of a detailed description definition. Okay, that's what you're looking at there. Now, here's one other concept that gets brought up. Complement. All right, the complement of an event is basically the polar opposite of what you're looking at. Okay, so this says the sum of all probabilities. So the complement of an event E, where all those events happen, is how many times did it not happen? All right, so if something happened 8 times and you did it 10 times, then the complement is 2 because you're just looking at the difference. All right, so the complement of what did happen is what did not happen in that given, as it says, sample space. So sample space is like how many total times did you see it, test it, or give it a try. Okay? Okay. All right, and the last little thing that we're going to go over here is the geometric probability. This is when they give you a shape, and oftentimes they'll just shade in part of the shape and say, what's the probability of you landing in the shaded part if the whole shape is used? Okay, and so what I mean by that, actually, we're going to have an example problem where we look at one of those. It's right over here. So here's just what I mean. Here's the whole given space. What's the probability, maybe that you don't land in a shaded spot? Or if you have the whole given space, what's the probability that you do land in just the shaded spot? Okay. And so when we're working out one of those are all theoretical because you can't just determine it unless you do it. That's the experimental part. And it's all about a ratio. Okay, so you're going to have a ratio of what you want, either unshaded or shaded, over the whole entire shape. And most of these deal with area. It's not like it's a guarantee every time, but most of these deal with the area of the whole shape on the bottom and then the area of just what you're looking for on top. Okay. So again, I said it already once, these problems take patience, they take practice, and you have to pay attention. All right, let's do some example problems. Let's get into it here. Okay, so we're going to start with kind of 3 miniature example problems. All right, so you have a red number cube, you have a blue number cube, 2 number cubes are rolled. If you ever forget, a number cube has 6 sides. So that's important to remember. A number cube has 6 sides, so the numbers 1 through 6 are always on a number cube. If it's a special number cube that has more than 6, they have to tell you that. But if all they use is the phrase number cube, it's 6. All right. If all numbers are equally likely, in other words, it's not some weird shape, what's the probability of each event occurring? Okay. So remember, the total number should be 6, all right? But we're going to work it out based upon some of these things like sum or difference, and then we'll get into like something that's greater. All right, so the first one here, what do we want? But remember, we have 2 number cubes, okay? So let's do this problem over here. We'll take some space. All right, remember, what you want goes on top, and then the total possibility goes on the bottom. So what if the sum is 6? All right. So when they say the sum is 6, that means that you are adding numbers together and they create the answer that is 6. All right. And if you are looking in the textbook, there is a great picture at the upper right-hand corner on page 803, all right? And if by chance you don't have your textbook with you, then you should just Google an image of what it would be for all the possible outcomes of 2 number cubes. And what I mean by that is you roll one, let's say you get a 1. You roll the other one, you get a 1. That's one possibility. And you need to work and figure out all the possibilities, but they give you a picture in the textbook. And if you don't have that textbook, look up an image through a Google image search, because this is going to save you a significant amount of time. So when you look at that image, when you look at that picture, you are trying to figure out how many different options there are to create a sum of 6. That would be 1 and 5. That's one. 5 and 1. That's another one. 3 and 3, that's 1. 2 and 4 is 1, and then 4 and 2 is 1. There's 5 total possible what you want outcomes out of a complete possible 36 outcomes. So this is our solution that we are looking for right here. 5 is what we want, 36 is the total. All right, the next one is the difference is 6. So now we're looking at subtraction. So the difference is 6. All right, now let's see. The difference is 6. Let's think about this. Let's use a little bit of logic because I had to read this one a couple times. The difference means subtraction. And if you only have the numbers 1 through 6, and obviously they're all positive numbers, we're not getting weird thinking there's a negative number on a dice. There are no possibilities. So this was one where when I first looked at it, I immediately started thinking, okay, yeah, what do I have to do? There's no way to create 6. The only way would be if you have numbers bigger than 6. So this is actually none. All right. There are 0 possibilities of creating, so in other words, 0, because you have to have a number bigger than 6 to find the difference, subtraction, to have an answer that is 6. In other words, like what if we went up to 7? Okay, 7 minus 1, I could get 6. But remember, a dice only goes up to 6. So this was a bit of a trick. This is where the words are so important. And sometimes logic also. All right, last one here with the intro problems. Okay, the red cube is greater. All that means is when you roll the dice, the probability that the red cube is actually bigger than the blue cube. That's where this picture comes in so handy in the textbook or Google image that, okay? So when I looked at that picture, everything I kept finding, I was able to find 15 different possibilities where the red cube could be bigger than the blue cube over a total of 36 possibilities. And now a probability must be reduced. If it can be reduced, it must be. So that drops down to 5 over 12 is the probability of each event happening. Okay, so there's 1A through 1C all worked out. Simple number cubes. These are considered to be the intro ones. Okay, so you got to understand these. You got to get good at these. Let's move down into number 2. Okay, now we're looking at 2 integers. All right, that just means it's a number. An integer, it's a number. Now here's your possible selections from 1 to 10. All right, an integer from 1 to 10. Actually, 2 integers from 1 to 10. They're randomly selected. All right, the same number may be chosen twice. What's the probability that both numbers are less than 9? So let's start by writing out what is this saying here. All right, this is asking for the probability, capital P, of both numbers less than 9. Okay, now here's what this looks like because you have 2 probabilities that are actually occurring here because you are selecting 2 numbers. So we have the probability of a number less than 9 times the probability of a number less than 9. All right, now the number is able to be chosen twice, and that is okay because we can find any value less than 9. They can be 8, 8, 7, 7, 6, 6, all the way down. The same number chosen twice, both less than 9. All right, so what is our total possible? It's 10. All right, there's 10 numbers that we're choosing from. So our total possible is 10. How many numbers are there less than 9. It doesn't say equal to 9, just less than 9. There's 8. 1 through 8 is less than 9. So there we go again, because you could pick that same number twice. That's what they want. So 1 through 8, 8 over 10, 8 over 10. Always remember, reduce your fractions. So 4 over 5, 4 over 5. Now, we multiply them together. You got to remember what we did from the prior section. This is a combination of the fundamental counting principle with probability. So remember, the fundamental counting principle was just get that and multiply it by the next possible option. So we're getting the probability of picking one number less than 9, 8 over 10. You can pick that same number twice. So there's another 8 over 10. Both of those probabilities have to be multiplied together. Now you're looking at 16 over 25. And remember, guys, this takes practice. All right, so you're going to need repetition and practice and really pay attention to these notes. All right, let's work on number 3. Okay, we have a DJ. All right, so some guy working at a radio station here maybe randomly selects 2 of 8 ads. All right, so there's 8 possible ads. He randomly selects 2 from that group of 8 to play before the show starts. 2 of the ads are by a local retailer. Okay, so think of a store that you know that's just right down the street, local retailer. What is the probability that she will play both of the retailer's ads before her show? There's a total of 8 ads that this DJ can pick from. A total of 8. 2 of these ads are from a local retailer, same retailer. What is the probability that she randomly selects those 2 ads to play before the show from that total of 8? So this goes back to thinking, is this a combination or is this a permutation? Now, quick review. Permutation is when order matters. Order is important. Combination is when order doesn't matter. What is a key word that I see here? Randomly selects 2. There's a total of 8. She just randomly selects 2. That tells me that order doesn't matter. She can pick any of the ads, doesn't matter. She picks 2 ads. It's not like you have to pick in alphabetical order, longest ad, shortest ad. There's no qualifications on how she picks. She just randomly picks. Combination, order doesn't matter. Now you got to think back, how do we write those combinations? By putting the biggest number in front, combination, smaller number second. Remember how we do this in the calculator? You put 8 and go math probability combination, then put 2, then hit enter. And what you will get from this is 28. Now, what we gather, though, is that this isn't the final answer, though, right? All right, if she randomly selects 2 from 8 ads, there's 28 possibilities, all right? There's 28 possibilities that she could gather. But now the further question into this problem is that both of those ads are from the exact same retailer. Now comes the second part to this question. How many different ways are there to pick the same ads from the one retailer? There's only one way. So there's 28 possible combinations, but there's only one combination that comes up when you pick those ads from the same retailer. So your final answer is actually 1 over 28. 28 is the total possibilities for all these combinations, but there's only one possible combination where you pick both from the same retailer. That's why the final answer is 1 over 28. All right, that's your favorable outcome. Okay, let's do number 4 here. This is one of the geometric shape ones. All right, so the probability that a point chosen at random inside the large triangle is actually in the small triangle. So that means we need to figure out this, which is favorable, compared to the total triangle, which is the full total area. All right, so the total area, total goes on the bottom, and then small triangle goes on top because that's what we want. We want it to be within the small triangle. It's just that the small triangle is in the entire big triangle. So what is the area of the smaller triangle? 4 times 4. Then divide that by 2. Remember the area of a triangle, base times height divided by 2. So that's going to be 4 times 4. All right. And so let's see. I want to make sure I have my problem worked out here. All right. So we're getting 16 over 225. Okay. So probability that a point chosen at random is inside the small, though, right here, but that small is within the whole triangle right there. Okay, and that one, I believe we just leave as is, 16 over 225. Okay, last one. All right, I know, long video. These are longer just because I want to make sure you get all the directions possible. Let's finish it out here. Last one. Okay. We have a table below, shows the 4 different suits from a deck of cards: heart, diamond, club, spade. By the way, we're going to be doing multiple problems throughout this chapter that deal with cards, so you probably want to start remembering how many cards are in a deck of cards. All right, so the table shows the results of choosing one card from a deck of cards, recording the suit, and then replacing the card. What does that mean, replacing the card? That means you put the card back in the deck. That's important to remember here. All right, so find the experimental probability because they did this. All right, so this was, let's say someone actually did this. This was real. They had 52 cards. That's how many cards are in a deck of cards, 52. And the table shows the results of choosing one card from the deck. There were 5 hearts that they put out, then they picked 9 diamonds, and then 7 clubs and 5 spades. Find the experimental probability of choosing a diamond. Simple enough. All right, let's see. Choosing a diamond, that's going to be easy enough, right? Because they tell us how many diamonds did they pick. They picked 9 diamonds. That was real. That was what they wanted. That was that was what they picked. And how many total cards, though, did they pick? Not 52 cards in the deck. They didn't do this 52 times. How many times did they do this? 5, 9, 7, and 5. 26 times. All right, so it's not to say that they picked 52 times. That would be every single card. They just did this 26 times, and this is what happened after 26 picks. So 9 diamonds out of a total of 26 cards picked. And there you go. All right, so we'll zoom out. There are example problems 3, 4, and 5. And here are example problems 1 and 2. All right, guys, ask those questions. Make sure that you are staying focused. Stay with me. And let's throw in another random question here to get some extra credit coming your way if you follow all of my note videos. Okay, let's see. Okay, this is an easy one. All right. You have Andy Dwyer. What is his real name? That's his character name, Andy Dwyer. What is his real name? All right, there you go. I will see you guys in class in the next video.